Hi, everybody. So in this video, I'm going to be talking about transformations and specifically linear transformations, as they're the only transformations we're ever going to talk about for the course. And then I'll give you a few examples of linear transformations and at least one example of something that's not a linear transformation. It is a transformation, though. When you say transformation, you're just talking about a function. It's just a function that goes from, in this case, one space into another. For us, the spaces are Rn spaces. So a transformation is a mapping that goes and assigns to every vector in Rn a unique vector, T of, in this case, T of u in Rn. We'll use the notation T goes from Rn to Rm in order to define the name of the function T and to define the beginning space in the target space. Now, if in addition, this function will distribute through vector addition and will distribute through scalar multiplication, the scalar can come out, then we say that that transformation is a linear transformation. We need these two properties at a minimum in order to say that linear transformations in one space gets mapped to a linear combination. A linear combination in one space gets mapped to a linear combination in another space, where here the scalars are used in both linear combinations are exactly the same. Now, there's a bunch of other things here that you need to know. One is that if you go and take a vector u in Rn and you compute T of that, there's a name for that. It's called the image of u. It's also given other names. It's called the output of T, of u under T. It's another way to say the same thing. There's other things too, you know, from functions that, for example, this beginning space is called the domain, but you don't really hear this next word very often. You, of course, hear range. Range is just the set of all images. It's just the mapping the function on every single set in the domain space. And that has to be a subset of the other space, Rm. The thing is, though, is that mapping into different spaces makes a difference for us now. Think of it as there's a difference between saying a line in 3 space and a plane in 3 space. A plane would kind of chop 3 space in half, a top and a bottom, to separate it, while a line does not. You can't separate the 3 space with a line only because you can just go around the line. So there definitely is a difference between the range and the ambient space you're going into. So we need a name for that guy too. It's called the codomain. So the domain and the codomain, that's the domain is the set you're coming from. The codomain is what you map into. If you want the set of all mappings, that's the range. Again, in algebra, you never ever probably heard the word codomain because you just don't need it really in that class. But now we really do, to make sure you understand the differences, at least geometrically. So at least you have one easy example. Every single matrix then will automatically define a matrix transformation, and all matrix transformations are all mapped with linear transformations. Seeing why that's true is incredibly easy. I just did it basically because since matrices distribute through vector addition and matrices kind of distribute through scalar multiplication, any transformation defined by matrix multiplication on the left-hand side is automatically a linear transformation. So matrix transformations defined by matrix multiplication is automatically a linear transformation. But notice what we don't know is it true that every linear transformation from Rn to Rm is actually also a matrix transformation for one matrix? Well, we don't know that, but what I can say though is that if there is a matrix transformation, there's a unique matrix for it. There's only one matrix that defines that particular transformation. So since there's only one, we can then say then that the matrix should be given a special name, and we call it the standard matrix for the transformation. So then if T is the mapping, then T with brackets around it to kind of hint at matrices, T with square brackets around it, that is called the standard matrix of the transformation. And we have this nice notation that if T of u is V, that the standard matrix, when applied as a multiplication to the left of the vector u, you will get v. So these two things imply each other. So t is the function, the name of the function. But the t with the brackets around it, that's a matrix. And you can multiply it on the left to the vector u to get the vector v. Obviously, then, if you do have a matrix transformation, T sub A, then the standard matrix for that transformation is just the matrix A. Now, you need a couple examples. So I'm going to go over a couple, and I'll ramp them up in difficulty to show you the type of things that you can do to try to figure out, well, how do you figure out what this transformation would be? So let's suppose that we have a transformation that sends each point to its reflection in the line y equals x. First, I don't know if this thing is a linear transformation. It's obviously a transformation. It's just a mapping. It goes from here to there. So then that's not a big deal. I want to know, is it linear transformation? And then even better, do I know if it's a matrix transformation? So here's a picture diagram to show you how the mapping works. It sends the point xy expressed as a vector to the point yx, again, expressed as a vector. So the mapping literally just does this. It sends f of xy to the vector yx. I want to know, is that thing a linear transformation? Well, one way to do that is to just check the properties, right? To take f of a vector plus a vector and show it's the same as f of the vector plus f of the other vector. But that's a pain. No one likes doing it. It's awful. So instead, we'll notice this little trick. If I can show that this particular transformation is actually a matrix transformation, it's defined by multiplying the vector xy on the left by some matrix, then if it's a matrix transformation, it's instantly also a linear transformation. So all I have to do is to figure out, can I somehow discover that the right-hand side, the vector yx, is really just some matrix times the vector xy? Well, here's a standard way to do that. Notice that you can write that vector yx as a linear combination. It's a linear combination of the vectors 0, 1, and 1, 0 using the scalars x and y. But then you remember that a linear combination can be represented as matrix multiplication, where the columns of that matrix are just the vectors being used. So that shows then f of xy is really the matrix 0, 1, 1, 0 times xy. So yes, f actually is a matrix transformation. Its standard matrix is right here. And since it is a matrix transformation, it's instantly then a linear transformation. That's great. That's great. So then this particular transformation is a linear transformation. It therefore will preserve our ideas of linear combinations. Let's do it again. So this time I want to know, what about projection? So let's project points upon the x-axis. When you do that, that's obviously a transformation. You're going from R2 to R2. You're mapping points to points. So then it's obviously it's a function. We want to know, though, is it a linear transformation? Well, here's a picture of it to show you how it works. You take the point xy and you map it to the x-axis. So that means that has to be the point x comma 0. Well, to do so, notice that you can define the function this way. This is the exact mapping. I want to know, is that a matrix transformation? Because if it is, it's instantly then a linear transformation. That would be great. Well, to do that, you could, of course, just check the properties. Take px of u plus v and show it equals px of u plus px of v, and then do the same thing for scalar multiplication. Take px of c times u and show it's equal to c times px of u. That's really a pain. It's really awful. And if we don't have to do that, we don't want to do that. Luckily, though, for this transformation, we don't have to, because I can very easily show you that this particular linear transformation is a matrix transformation and is therefore a linear transformation. So let's just do that. But same trick. So we see what the mapping of pxy is under the mapping p of x. So the vector xy under the transformation p of x is sent to the vector x0. So I'll just notice that the vector x0 can be written as a linear combination using x's and y's as the scalars and the vectors being 1, 0, and 0, and 0. But we also remember, though, that linear combinations can be represented by matrix multiplication. In fact, it's the matrix 1, 0, 0, 0 times the vector xy. So then, yeah, that makes it be a matrix transformation. I showed you how to find out the image of the vector xy by just multiplying the vector xy on the left by the matrix 1, 0, 0, 1. So the standard matrix for that particular transformation is the matrix 1, 0, 0, 1. And by a comment I've already shown you, or I talked about, since it's a matrix transformation, it's instantly a linear transformation. That's great. So far, pretty easy. Let's do one that's quite a bit more complicated in order to ease into the next topic. So this time, the transformation is going to take a point. It's going to rotate it counterclockwise through an angle of theta degrees about the origin. This is clearly, once again, a transformation because it's just mapping points in the plane to points in the plane. That's certainly a mapping. But I want to know, is it a linear transformation? This time's a lot harder. I can't like draw a nice picture for you. So instead, what I'll do is I'll do it symbolically. We'll need a little bit of trig. So then let's say r of theta, r sub theta applied to u. So I'm going to take the vector u and I'll draw it in standard position. So I've done that down here for you. When you do so, that vector has an angle, alpha, that you rotate counterclockwise from the positive x-axis to get to it. There's also a length to that vector. If you remember, every vector in the plane can be, well, every vector everywhere really, can be represented as a length of the vector times a unit vector. It just so happens that the cosine of alpha, the sine of alpha, is a unit vector that describes the direction of the vector u. And of course, the length of u is the length or the magnitude of that vector. So I can represent that vector by what you see right here. That's the vector u, just written a different way. This is useful because then I can separate length of the vector and the angle that describes the direction of that vector. Let's just go ahead and rotate that vector counterclockwise through an angle of theta. When I do so, the new vector has to be as you see right here, because the length of the vector, since it's a rotation, the length of the vector can't change. The angle has changed though. It's gone from alpha plus theta amount of rotation. So the new direction has to be cosine of that angle, sine of that angle. So I now know what r theta, r sub theta of u is. It's got to be this strange looking vector. What I want to know is there some way to represent this as matrix multiplication to the vector u? There is. It's just we got to do a lot of little sneaky trig and remembering facts about matrix multiplication. So one is, we know that the cosine of a sum of two angles can be expanded, and the sine of two angles can be expanded by using the angle addition identity. So I did that for you there. When you see in the vector a difference or sum of products, you should think dot product. Dot product means matrix multiplication. So you got to figure out what it is. And in fact, it's this. If you take the product of this 2 by 2 matrix with the vector cosine of alpha, sine of alpha, you get the above a vector. But then you also remember that the length of u is just a scalar. It's just a scalar. You can put that scalar anywhere you like. So I'll move it and I'll multiply it to the vector cosine of alpha, sine of alpha. But then you remember that the length of u times that vector, that's just the vector u. So therefore, I just showed you that the rotation counterclockwise about the origin through an angle of theta in degrees or radians of the vector u can just be done by matrix multiplication of the matrix cosine of alpha, cosine of theta minus sine of theta, cosine of theta multiplied with the vector u. So that means then that this transformation is a linear transformation because it's a matrix transformation, and I gave you the standard matrix. Now, clearly, what I'm trying to lead you up to is to think of things you've seen before in your life where this is necessary. Any computer game ever. I've actually, a lot of stuff you're doing right now on the screen, it's actually all linear transformations. Anytime you want to rotate something on a screen, you want to flip it, you want to project it, you want to crush it, those are all linear transformations. They're all done by matrix multiplication in a really clever way. And if you ever think about in things in 3 dimensions, seeing it in 3D, that's still linear transformations. There's a kind of a projection upon your screen. That's what you see. There is a 3D version, virtual version in the computer, and all it does is transform it, that image, and press it upon your screen. So this is all very important for computer graphics for sure. And of course, it's useful for lots of other things too. I think though what you need is at least one example of a transformation that's not a linear transformation. Now, what you can't do is say, well, I can't find the matrix, so it can't be a matrix transformation, so it's not a linear transformation. That's wrong logically on a couple levels. One is just because you can't find it doesn't mean it doesn't exist. It means you didn't have talent to. And also, just because it's not a matrix transformation does not mean it's not linear, because we don't have that logical connection yet. We only know if it is a matrix transformation, then it must be a linear transformation. We have that logic. We don't have the converse, or in this case, the inverse. So how do we go about showing that it's not a linear transformation? It's really easy. You just want to show some examples that violates the two properties. One of the properties is this one. If it was a linear transformation, then I would have that T of, let's say, the vector -1, 1. And by the mapping, that vector is vector absolute value of -1 and absolute value of 1. That's the vector 1, 1. And take the vector T of 1 and -1. That would then be the vector absolute value of 1 and absolute value of -1. That's also the vector 1, 1. But notice that the vector T of -1, 1 plus 1, -1, you can do the vector addition first to get the vector 1, 0, 0. And notice I'm actually not following my own rules. I should not be having, I should not have the parentheses around here or here. I don't need to do that. Oop, stop it. I don't need the parentheses here, and I don't need the parentheses here. I don't need the parentheses there. Well, no, actually there I do, because I have to emphasize that the addition comes first. That would then be the vector absolute value of 0, absolute value of 0, and that would be the vector 0, 0. So notice then, T is not a linear transformation. It's certainly a transformation. It's not a linear transformation. And that's because I found at least two vectors. So that T of the first vector plus T of the second vector, that did not equal T of the sum of those vectors. And that's what had to happen. Remember, that's one of the properties. It has to preserve vector addition, and it didn't. So there you go. That's a good example of where something is not a linear transformation. Pretty much, if you see any kind of operations on this, the components of the input vector, and if it's not linear, like if you're squaring the x, or if you cube the x, or if you take x times y somewhere, the result's incredibly likely not to be linear. It's incredibly likely to be not linear. So it's usually pretty easy to see that it's not linear. Once you know it's not linear, just almost always just pick almost any two vectors and go and take T of the first vector, T of the second vector, take T of their sum, and I bet you'll find that they're not equal in the end. That the sum of the images of the two vectors under T is not equal to the image of the sum of the vectors. And I believe that's enough for that portion.